Welcome back. So we continue with chapter 1, and in this video we are going to cover section 1.2 about linear bounded operators. Okay, what is a linear operator? A linear operator between two normal spaces, or just between two vector spaces if you like, is an operator or a function that takes sums into sums and a multiple of a vector into multiple of its image. Okay, so we can split this condition into two parts. So we can write L of x plus y is L of x plus L of y, and L of alpha y equal alpha L of y. So, and we can combine them into just one expression like this. So, and if you like, a linear map takes a linear combination into a linear combination. Now, just for a question about terminology, map, function, operator, mapping, same thing. Okay, don't make a big deal about the difference. Maybe in the past you distinguished between function and map or function and application, because a function has a domain and an application is defined everywhere. It should be clear from the context what do we mean actually here. So, okay, so a linear map, linear operator, same thing. Okay. Okay. Now, let me give several equivalent conditions that are equivalent to the continuity of, since if E and F are norm spaces, there's a topology on E and a topology on F, so we can talk about continuity of any map or operator between these two. So the conditions that I'm going to state are all equivalent. So first condition states that L is Lipschitz continuous, or just Lipschitz, which means that L of x minus L of y is less than a constant times the distance between x and y. And by the way, for linear, as you observed, instead of writing L of x between parentheses, when the map is linear, we just write Lx. So just to simplify the notation. So L of x or L of x between parentheses, same thing. Okay, so first condition states that L is Lipschitz continuous. Second condition, L is uniformly continuous. Third condition, L is continuous, so means continuous at every point. Fourth condition, L is continuous at the origin. Fifth condition, there exists a constant m such that the norm of L of x is bounded from above by m for every x in the unit ball of E. This is just the notation for the closed unit ball of E. So it's the set of x whose norm is less or equal than 1. Okay, and sixth condition, L maps bounded sets into bounded sets. So the image of a bounded set is a bounded set. And last condition, there exists a constant such that the norm of Lx is less than a constant times the norm of x. Okay, I put these into in some order actually, because as you know, Lipschitz continuous implies uniformly continuous implies continuous, etc. So 1 implies 2 is true even if the operator is not linear. So 1 implies 2, 2 implies 3, 3 implies 4. Now here we have some work. 4 implies 5. You have to, it's not trivial, but so you can prove, you can do a circular proof here actually. So 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies, etc. so on, and 7 implies 1 is pretty straightforward because L is linear. So you just replace x by x minus y and use the linearity. So you get the same constant actually here. Okay, so now all these conditions are equivalent to the continuity of the operator. And this is why a linear operator satisfying one of these conditions is called a bounded linear operator. Why we call it bounded? Because of property 6. Because it maps bounded sets into bounded sets. So for a linear map, boundedness and continuity are equivalent. Okay, so okay, now the space of continuous or bounded linear operators from a norm space to another norm space is a vector space actually. It's denoted by calligraphic L of E and F. Why it's a vector space? Because we can define the sum of two linear operators and a multiple of a linear operator. So we may denote it by calligraphic L of E and F or calligraphic B for bounded. Okay, and when the target space is equal to the source space, we just write L of E or B of E instead of L of E and E. Okay, just for notation. And now we can put a norm. We can turn this space of operators into a norm space by defining norm of L to be the supremum of the norm of L of X for X in the unit ball, in the closed unit ball. And this norm, this is really a norm, as you may check. And it's called the operator norm. So in principle, you saw all these results in second year. Okay, so this norm sometimes denoted by subscript L of E and F to emphasize that it's an operator norm. Okay, and we can also prove that there are several characterizations of this norm. So it's the norm of a linear bounded operator is also the supremum over the unit sphere. It's also equal to the supremum over the open unit ball. Okay, so these three quantities are equal. It's also equal to the supremum of norm of Lx over the norm of x for x different from 0. And it's also the infimum of all positive constants satisfying this inequality. And actually, we know that the norm of Lx is less than the norm of L times the norm of x. And so actually, the infimum is a minimum. Okay, so the norm of L belongs to the set. So this is really a minimum here. However, you have to pay attention that the supremum here, which is the definition, is not necessarily a maximum. It need not be achieved. Okay, and we can give several examples where the supremum is not a maximum. Okay. Now, let us recall some fundamental examples. The subnorm over the space of continuous functions from a compact interval AB into R, the subnorm, as you know, is, I defined it in the previous video actually. This is the supranorm norm of uniform convergence, right? And denote to each U in E, so to each continuous function from AB to R, define LU to be the antiderivative of U that vanishes at A. So otherwise stated, there's a formula for L of U. So for each x in AB, LU evaluated at the point x is just the integral from A to x of U of t dt. So as you know from calculus, LU is precisely an antiderivative of U because it's an integral and vanishes when x equal A because when x equal A, it's 0. So this is a fundamental example of a linear operator, as you may check, because integration is a linear operation, as you know, like derivation as well. So this is a very simple, the simplest example of an integral operator. Okay, and it's not only linear, but it's also bounded. And we can show easily that the norm of L is just B minus A. Okay, how do you prove that? Double inequality. Okay. If it's the first time you see this result, you can prove it as an exercise. Actually, it's not difficult. Just go back to the definition. But in principle, you encountered such examples in second year. So this is first a fundamental example. And more generally, instead of just integrating U, we can integrate U against another continuous function, phi. So if we fix a function phi, continuous function from AB to R, we let LU be the antiderivative of phi U that vanishes at A. So same definition, but we multiply by phi and integrate. So here again, we see, so linearity is trivial because multiplication is linear and integration is linear, so it's linear, but it's also bounded. And the norm of L, as you may check easily, is less than the norm 1 of phi, the one norm that you defined in the previous video. But actually, we can prove equality. So there is equality. So the norm of L is precisely the norm 1 of phi. Now, this is not totally trivial. If you want to prove that, I suggest that you... So how do you prove that? Double inequality. First one is clear. Second one, less clear. So you take a sequence un in the unit ball, defined by n phi of t over 1 plus n absolute value of phi of t. And after some computations, you may convince yourself that the norm of L is bigger or equal than the norm of phi 1. So we have equality, actually. Okay, so next example, the derivation operator. So we have to work in a space of smooth functions in order to talk about derivatives, because a continuous function need not be differentiable, but a C1 function has a derivative. So for u in C1, we let L of u to be just u prime. So this is the derivation operator. And of course, it's linear because derivation is linear. And it's also bounded. And as you may check easily, it's straightforward. The norm of L is less or equal than 1. But it's actually equal to 1. How do you prove that? This is less trivial. We have to consider a sequence, actually. So you can do it as an exercise, right? So if you consider this function, un of t equals sine nt over n, you evaluate the norm of un. So just compute un infinity plus u prime n infinity, and you do the work. Okay, so we can prove here that it's not always easy to compute norms precisely. Okay. And more generally, instead of differentiating u, we can differentiate u after multiplying it by some constant, by some function, which is as well C1. So again, we get a linear map which is bounded, and its norm, its operator norm, is less than the norm phi in this norm, same thing. And yeah, I don't know if equality holds. Yeah, maybe it's good. So I didn't think of. So you can think of this. I think you have equality actually here, but I didn't try to prove it. Okay, next result. If we have a linear operator between norm spaces, and if the source space is finite dimensional, then the operator is automatically bounded or continuous. Okay, this is something fundamental. Okay, so when you work between finite dimensional spaces, all linear operators are automatically continuous. So continuity is something that you don't need to check. But it becomes less trivial in infinite dimensional spaces. Okay, and so in principle, you prove that in second year. And there's no harm, once again, to reprove it if you like. Okay, and now, if the target space is a Banach space, then the space of linear bounded operators between E and F is also a Banach space. So if the target space is complete, the space is complete. And there is the converse actually is true, but it requires some tools from functional analysis that you shall learn next year. Okay, so I think you proved that. And third result, the composition of two linear maps, two linear operators, when it's defined, is also a linear bounded operator. And the norm of the composition is less than the product of the norms. Not difficult. Okay, just this straightforward. And often we shall write ST instead of S composed with T. This is very convenient. Why? Because if S is a linear bounded operator from E to itself, then we can write S to the N instead of S composed with itself N times. This is very convenient. And in this case, if we apply the previous result, we get that the norm of Sn is less than the norm of S raised to the power N. And for convenience, it's also good to set S to the 0 is the identity of the space in which we are working. This is just the notation for the identity of E, the identity map that to each X associates X. Okay, now a particular case is when the target space is just R, the set of real numbers. Then the space of linear bounded maps from E to R has a name. It's called the dual of E, and it's usually denoted by E star, sometimes E prime. Okay, and in functional analysis, such elements of LE and R or E star are denoted by F, but we can denote them by L, G, F, T, anything you like. Okay, and therefore, so if I go back to the definition, the operator norm in E star is just the supremum of the absolute value, because the norm on R is just the absolute value. Okay, so it's the absolute, the supremum over the closed unit ball or the unit sphere, same thing as we saw, and we can actually drop the absolute value, as you may check, because if X, because the unit ball is symmetric. Okay, so you can prove that you can drop the absolute value here. And it's also convenient, instead of writing f of x, to write fx between brackets, because the reason for this notation is that this is really a bilinear form, which means that it's linear in f and linear in x. Okay, so it's like a dot product, if you like. So this function is often used in functional analysis. Okay. And by a previous proposal, by proposition 1.9, a dual is always complete, even if E is not complete, because the target space R is complete, as we know. Okay. And here are some fundamental examples of elements in the dual. If we take the space of continuous function on a compact interval AB equipped with the sup norm or norm of uniform convergence, and we just take the integral of U. Now here, unlike the previous example, the bounds are fixed, so this is really a number. Okay, it's not a function. Okay, so this is really so F is a map from E to R, and of course it's linear, but it's also bounded, and as you may check easily, its norm is just B minus A. And of course, more generally, we can integrate against another fixed function, and in this case, the norm of the operator is the norm 1 of phi, and the proof is similar. So here we have double inequality. Okay, so the proof is similar to the proof of the previous examples. Just take next example, the evaluation operator at a point. So we take E to be the same space, and we fix a point in the interval t sub 0, and we let f of u to be u evaluated at t0. Then of course, this is linear in u, straightforward, and it's bounded as well. So you can easily check here that the norm of this operator f is 1. Very straightforward. So it's called the evaluation operator at t0, or the Dirac functional at t0, or the Dirac mass at t0. Okay, in honor of the great physicist Paul Dirac, who used such things. Okay. And last example that you probably know, if we take a real number strictly bigger than 1, and take p prime to be p over p minus 1. P prime has a name. It's called the conjugate of p, and it satisfies the relation 1 over p plus 1 over p prime equal 1. For example, if p equal 2, then p prime equal 2 as well. If p equal 3, then p prime is 3/2. Okay, and we now consider, we fix an element y in LP prime. LP prime, recall, it's the space of sequences. So y is a sequence actually, such that the sum of yn to the power p prime is convergent, right? And we define the map capital L from LP to R by setting L of the sequence X is this dot product. So take all the components and component by component and add them. And this makes sense because we have the famous Hölder's inequality, which tells me that the series is absolutely convergent because it's bounded from above by the norm P of X times the norm P prime of Y. This is called the Hölder's inequality. So the series is absolutely convergent and therefore convergent. And we see that the norm of L is actually less or equal than the norm of Y. And we may prove equality. Actually, we have equality. Okay, but it requires some work, not trivial. So this is an example of an element in the dual of LP. Okay. Okay. Now we come to the notion, the very important notion of isomorphism. Now, in algebra, you probably encountered the notion of isomorphism between vector spaces or between groups or between rings or fields. In any field of mathematics, there is the notion of isomorphism. Generally speaking, an isomorphism is a map function that conserves the structure under consideration. For example, in group theory, an isomorphism, first of all, it should be a bijection. So it should, okay, so in group theory, an isomorphism is just a bijection which conserves the operation. So f of xy is f of x times f of y. In vector space theory, an isomorphism is just a bijection which is linear. Now, the inverse is automatically linear, as you know. Now, in the field of functional analysis or Banach space theory, we have, because a norm space has an additional structure. It's a vector space, of course, so it has an algebraic structure, and it also has a topological structure. So an isomorphism should conserve both the algebraic structure and the topological structure. So an isomorphism of norm spaces, or a topological isomorphism, is a linear bijection from E to F, which is continuous and whose inverse is continuous as well. Okay, so it's both an algebraic isomorphism. So the usual isomorphism of between vector spaces, which I call it algebraic isomorphism. Distinguish between the two kinds. Okay, so an isomorphism of norm spaces is both an algebraic isomorphism and a homeomorphism if you study topology. Okay, so it conserves both structures, the algebraic structure and the topological structure. So this is what you said. So two isomorphic norm spaces have the same algebraic and the same topological, and therefore we can, as usual, identify them. Okay, and this is what I was saying, that this concept of isomorphism is very broad in mathematics. And for example, for an algebra is the group of symmetries of an equilateral triangle and the group of permutations of 1 to 3 are isomorphic as groups, so we can identify them, as you may know. Okay. By the way, this group has 6 elements, right? 6 factorial. For a topologist, a circle, an ellipse, a square, and a triangle are all homeomorphic. So topology does not distinguish between these shapes. Okay, and we talked about this last year. For a functional analyst, all n-dimensional spaces, like norm spaces, are isomorphic. Or all separable Hilbert spaces, as we shall prove maybe next year, are also the same object, so we can identify them. Okay. So because it's very important to understand that two finite dimensional spaces are isomorphic, even algebraically, if and only if they have the same dimension. Okay, this is very important. So isomorphisms conserves, among other things, the dimension. It's very important to this. Okay, so for example, there can be no isomorphism between R and R2, even if you don't require continuity is automatic, but here it's impossible because R has dimension 1 and R2 has dimension 2, so cannot find any isomorphism between the two. So a useful notation, if E and F are isomorphic, then we shall use this symbol. Okay. And the set of isomorphisms. So here in this course, isomorphism, we will mean topological isomorphism or isomorphism of norm space, okay, because continuity is very important in this course. So the set of isomorphisms between two norm space E and F will be denoted by isom of E and F. And pay attention, this set could be empty. And this happens if and only if E and F are not isomorphic. Okay, so this set, it's possible that E and F are not isomorphic. One of the problems in functional analysis is the classification of Banach spaces up to an isomorphism. Okay, but we shall not deal with this in this course. But you have to, like in group theory, one of the problems is the classification of groups. In topology, one of the biggest problems is the classification of manifolds, and so on. And of course, if the target space is equal to the source space, we write isom of E instead of isom, just to simplify a little bit. Now, here are some results. If two normal spaces are isomorphic, then either they are both complete or both incomplete. So a Banach space cannot be isomorphic to an incomplete space. Okay? And this is straightforward because you just reason by Cauchy sequences and you use the definition. Now there is a stronger notion of more rigid notion of isomorphism. It's that of isometry or isometric isomorphism, because the terminology is not unified among mathematicians. Some people call isometry what other people call isometric isomorphism, and I will tell you why there's some difference. Because this is my definition. In isometry, between two norm spaces is a linear operator that conserves the norm, okay? But we didn't say that it's bijective or surjective. Of course, in isometry is injective. Why? Because of this. Because if L of x is 0, then x is 0. So the kernel is trivial. So in isometry is necessarily injective, but not in this definition, we don't require the surjectivity. Now, if it's surjective, and of course it's automatically continuous, as you know, and the norm is 1, okay? And observe also that in isometry conserve the distances, because L is linear, should just replace x by x minus y, and so we have conservation of distances. Okay, whereas in isomorphism does not necessarily conserve distances. Okay, it may distort distances. Okay, so think always in the finite dimensional case about matrices or geometric transformations. So, for example, rotations about axes or points conserve distances, but homotopsies or other kinds of transformation do not conserve distances. Okay, so you can think of in isometry as being a generalization of the concept of rotation, if you like. And so an isometric isomorphism is both an isometry and an isomorphism. So it's just a surjective isometry, if you like, put in a different way. So an isometric isomorphism is a surjective isometry. Okay. Now, some people, when they say that E and F are isometric, it means that there are isometrically isomorphic. Okay. So just to have to pay attention to these small details. Okay. So we shall use this notation to denote isometric isomorphisms. So compare with the previous one. So we just put here two horizontal inequality sign, if you like. So we have two concepts. So of course, an isometric isomorphism is an isomorphism, but the converse is not true. Okay, and this is what. Okay, so this is more rigid. Okay? We don't need it more all the time. So isomorphism will be enough for us. And here I'll give 3 examples. The first example I will give it in the form of an exercise, because in usual classrooms days, I let the students solve some exercises or write a part of the proof of something in order to not be bored with lengthy lectures. But it's impossible now here. So, okay, so first example is that the space of linear bounded operators from R into a norm space E is isometric to E. So we can identify these two. And this is what we shall do later. Okay, so here's one isometry. So call it T. T is an operator between E and L of R and E that to each vector x in E associates a map, because an element here is a map, is a linear map. And it's automatically continuous actually, because R is finite dimensional. So we don't need to bother to check continuity. So this map actually just associate to each real number small t the vector dx. Okay, so and now I claim that this is the required isometry. It's straightforward. But first, we just need to check that t is well defined. And what I mean by that is that tx is really here in this space. How do I know that tx is here? It should be linear, right? Linear in t, and this is straightforward actually. It's linear in t and x as well. Okay, so we don't need to check continuity, it's automatically continuous. Okay, but you can check if you like. T is linear in x, so it's linear in t and in x if you like. So t of x plus y is just t of x plus t of y, and t alpha x is alpha tx. Pretty straightforward. And t conserves the norm. So the norm of tx is the norm of x. Just go back to the definition and convince yourself that we have conservation of the norm. And this implies actually, as we observed, that t is injective, because if tx is 0, then x is 0. So you don't need to check that t. You can check if you like, but you don't need. If you prove that, then it's fine. And t is surjective, and the operator is actually very easy to write. It's easier than t. So I could have started with this operator, that to each linear map from R to E, G, I associate its value. So it's just an evaluation operator actually at 1. So you may easily why? Because what is x from this map? X is when I put here t equal 1. Okay, so keep this example in mind because you shall use it later. Okay, so it's very straightforward, but you can write the details. Okay, so this is what we have to. So T is an isometric isomorphism between the space of linear bounded maps from R to E and E. Okay, second example. Let's consider an integer bigger or equal than 1 and equip Rn with some norm and fix a basis of Rn. And consider the space of square matrices of size n. Call it Mn of R. And now this is a vector space, as you know, the space. And by the way, what is the dimension of this space? It's n squared, n by n. Right? So put this norm, the operator norm, on Mn of R. So the norm of a matrix is just the supremum of the norm of A multiplied by a vector x when x runs varies in the unit closed unit ball. Okay, and this is the norm. This is the same that I fixed here. Okay, so don't confuse this norm with this norm. This is the operator norm, and this is the norm of a vector in Rn. So it could be, for example, the Euclidean norm. And now, so we have a norm, and now we equip the space of linear maps. Of course, they are, as we said, automatically bounded because Rn is finite dimensional. So the space of linear maps from Rn to Rn, or the space of all linear bounded maps from Rn to Rn, we equip it with the usual operator norm. So what do we have here? We claim that this space of linear maps from Rn to itself is isometric actually to the space of square matrices of size n by n. Okay, and this should not be a surprise because we can always think of a linear map as a matrix. Okay, and the isometry is very straightforward. It's just we associate to each linear map its matrix in the basis P. So it depends on the basis actually, because if you change the basis, the matrix changes. Okay, it's the same operator, but its matrix may change if we change the basis. Okay, so each column of the matrix actually is what is our. So the first column contains the components of the image of the first element. Okay, so for example, if L of E1 equal alpha 1 E1 plus alpha 2 E2 plus alpha n En, so the first column will contain alpha 1, alpha 2, etc. alpha n. So we studied this in linear algebra. Okay, so we have as you may check easily, this just straightforward actually. Then we have an isometric isomorphism. So we can identify the space of linear maps from Rn to Rn with the space of matrices. Third example, an isomorphism which is not an isometry, just a homotopy of center 0. Okay, so if you have an normal space and lambda a number different from 1, and you consider the homotopy of center 0 and ratio lambda, then we have an isomorphism, but it's, and of course, different from 1 and different from 0. Because if lambda is 0, this is not an isomorphism at all. So lambda should be a real number different from 1 and different from 0. So it's not an isometry because distances are distorted by a factor lambda. And the last example of two isomorphic spaces that are not isometric, the same space Rn, but equipped with two norms. So there's an error here. This is the norm 1, this is the norm 2. Okay, the one norm, sum of components, and the Euclidean norm. So here, as you may easily check, they are isomorphic, but not isometric. Okay. Why? Because as you may know, the unit ball with respect to norm 1 looks like a cube, a rotated cube. And a cube cannot be transformed into a round sphere with a linear map. Okay, so it cannot be an isometry between the two. Okay, this is the ideal. So this concludes the list of examples of isomorphism and isometries. And by the way, if you find this video lengthy, you can stop the video now and watch it, continue watching it later. Okay, but I will continue. And we have now a very important and deep theorem of functional analysis called the Banach isomorphism theorem. Okay, it concerns the continuity of the inverse of a linear map. If we have two Banach spaces, so here the assumption of completeness is very important. Okay, so both spaces should be Banach spaces. If a linear map between A and F is continuous and bijective, right, then automatically the inverse is bounded or continuous. And so TB is the isomorphism between A and F. Okay, and as we said, both spaces should be Banach spaces because a Banach space cannot be isomorphic to a non-Banach space. Now, this is not trivial. Okay, because you encounter in topology continuous bijections which are not homomorphisms. Okay, but here actually, so the result is not trivial, and we usually prove it next year in math in the course of functional analysis. So it's not part of your program now. Okay, because you have to establish several preliminary facts. So it's a deep theorem, but we shall use it. Okay, so we don't need to worry about continuity of the inverse if you are working between Banach spaces and the operator is bijective and continuous. Okay, and once again, it's very important to assume we need the completeness assumption. This is one, the first place where we need the completeness assumption. Okay, because some results in this course are not true if we remove the completeness assumption, and we can give counterexamples. Okay, and now I move to the study of the space of the set of isomorphism between two Banach spaces. But to motivate the idea what we are going to do, by a previous example, we know that the space of linear map from R to R can be identified with R. Okay, so just take E equal R in the previous example. So what does this really mean? It means that, because what are linear maps from R to R? Linear maps from R to R are just lines through the origin. And a line through the origin is characterized by its slope. So the identification here is just like identifying a line through the origin with its slope. The slope is a real number. Okay, so this is the idea. It's not really difficult. So the isometry, as you know, just by special case of the previous example, so take E equal R, the isometry from this space to the space in the previous example was denoted by T minus 1, and it was just an evaluation operator at the point 1. Okay, so you evaluate a linear map with its value at the point 1. Okay, it's very simple. So if you solve the previous exercise, you would have noticed that why this is true, because if x is a real number, then we can write x is x times 1. And since x is a real number, we can put it outside and you get x times g of 1, which is just a multiple of x. Okay. So, okay. So if we identify L of R with R, what is the set of isomorphisms between R and R? It's very easy. So an element, a linear map from R to R, is bijective if and only if what? It's not horizontal. So it means that its slope is different from 0, right? So G is bijective. So of course, if it's bijective, the inverse is linear and automatically continuous. Okay, so G belongs to the isomorphism, to the set of isomorphism of R if and only if G at 1 is not 0. So otherwise stated, this isometry that takes L of R into R takes the set of isomorphism of R, so the set of lines, not non-horizontal lines, if you like, into R without 0, or R star, if you like. But I wrote R without 0 because R star could be used to denote the dual of R, which is the same as R, by the way. So basically, the set of isomorphism of R is just minus infinity 0 open union 0 infinity open. So the set of non-zero numbers. Okay. And what can you say about the set? The set is open, as you may know, because it's the union of all two open intervals. And another way to see this, that if you consider, it's very important actually. How do you know that a set is open in some topology, in some metric space, or in some norm space? If you take a non-zero element and add to it a very small element, then the resulting number will be different from 0, as you may check. So this is what we call stability under small perturbations, which is just the openness condition. Okay. So if you take a positive element, even if it's very small, and add of it half of it, then the result will be, or subtract half of it, the result will be strictly positive, and same thing if it's negative. Okay. And more generally, if we identify L of Rn, the set of linear maps from Rn to Rn with the space of square matrices, then what is the set of isomorphisms between Rn and itself? it's just this set of invertible maps, invertible matrices that we denote usually by GL of N and R. It stands for general linear group or group lineaire. Okay, so here we can identify the set of isomorphisms of Rn with the set of invertible matrices, or the matrices with non-zero determinant. And once again, you probably learn that this set is open in this space Mn of R. And this means precisely what? This means that if we have an invertible matrix and perturb its elements with small, so if we change a little bit the entries of the matrix a little bit, the resulting matrix will still be invertible. Okay, so this is another way of seeing the notion of openness. Okay, and now we would like to see if this result is still true in the more general context of Banach spaces. Okay, so is it true that the set of isomorphisms between two Banach spaces is an open subset of the space of linear bounded maps from E to F? And the answer is yes, it's an open set. So once again, what does this mean? It means that if you take an isomorphism between E and F and add to it a small operator, an operator with small norms, with small norm, then the resulting operator will still be an isomorphism. Okay, so it's the first step toward the theory of linear perturbations, if you like. Okay, but to prove this, we need to establish a preliminary result, which is very interesting in its own. It's a generalization of the geometric series. So you know, if x is a real number or even a complex number with modulus less than 1, then 1 over 1 minus x can be written as this geometric series. But so I underlined this condition because, as you know, every power series has a radius of convergence, and the radius of convergence in this case is 1. So it's very important, and we shall encounter this restriction now in the more general context. Why 1? Because actually, if you forget this condition and just write this without any care, and you put x equal 2, for example, you'll get 1 over 1 minus 2, which is minus 1, is 1 plus 2 plus 4 plus etc., which is plus infinity. So you get minus 1 equal, or minus 1/2, sorry, minus 1 is plus infinity, which is nonsense. So it's very important when dealing with convergence sequences to pay attention to the domain where they converge. And so the first, so as we said before, the identity of a norm space E can be denoted by I sub E or 1 sub E or just 1 if there's no confusion. And this is the generalization of this geometric series, is that if you have a Banach space, so once again, we need the completeness assumption here. If the norm of a linear bound operator from E to itself is less than 1, then the identity minus S is an isomorphism, and the inverse is given by this geometric series with general term S to the N. S to the N, once again, is what is S composed with itself n times. And this is not difficult, actually. So the first, let us establish the convergence of the series. And this does not happen if the space is not complete, as we shall see, because if the norm of S is less than 1, then the geometric series of real numbers, whose general term is norm of S to the power n, is convergent because it's a geometric series. Okay, just put x equal norm of S. And by the comparison test, since the norm of S to the n is less than norm S to the power n, the comparison test for a real series tells me that the series whose general term norm of S to the n is also convergent as well. And this means that the series Sn of general term Sn is normally or absolutely convergent. And here now comes the completeness assumption. In a complete space, a normally convergent sequence is convergent. Okay, so we ensure the existence of this series, the convergence of this series. First step. So we denote T. We denote by T the sum of this series. So T is the the sum from n equals 0 to infinity of Sn. So what does it mean? It means that T is the limit of the sequence of partial sums. Okay, so by definition, T is an element. So S belongs actually where? S is in L of E. So and so the series converges to an element in L of E if it's convergent. By definition of convergence, the sum, the limit, is an element in the same space. So if this is a series in L of E, then the sum is in as well as in L of E. So T is just an element in L of E. Okay, and now if we use the continuity of S and T, then okay, just take T equal this and multiply to the left by S. And by continuity, you can put S inside. So you get S times Sn. And same thing if we multiply to the right. So if you multiply the series from the left or from the right by S, we can put S inside, and then we get a series of Sn plus 1, right? And this is just the series, the geometric series, but starting from S, not from the identity. And now we are almost done, because now if we multiply T by 1 minus S, or the identity minus S, we get T minus Ts. But T, recall that T is just the geometric series starting from 0, and Ts, as you observed, is just the geometric series starting from 1. And when I do the difference, we just get what? The first term. And the first term is just the identity, because the series starts with the identity, or S to the power 0. And same thing if we multiply the identity minus S to the right by T, so we get the same thing. So what does this mean? It means that T is the inverse of IE minus S, and T is just the geometric series. So we prove that it's invertible, so it's bijective, and continuity is automatic here, right? Actually, we know that it's continuous because T is continuous, right? So don't need to. Okay, so we don't need to invoke the Banach isomorphism theorem actually, because the inverse, these two equations actually prove that the identity minus S has an inverse in L of E. Okay, so it's linear and continuous. So we have now an isomorphism, and that's it. So this proves the preliminary result. Okay, now we go to the last and the main result of the section. That tells me that if we have two Banach spaces, then the set of isomorphism between these spaces is an open set in the space of linear bound maps, and the map or operator, not linear, that to each isomorphism as associates its inverse is a continuous map between these two spaces. And as you observed, so proof, the set of isomorphism as you observe could be empty, and this happens if and only if the two spaces are not isomorphic. So in this case, there's nothing to prove. Everything is empty, so the whole discussion is empty. So we assume that the set of isomorphism is not empty, and we pick a point in the set of isomorphisms as sub 0, and I claim now that the ball in this norm space of center as 0 and radius 1 over the norm of the inverse of S sub 0. So this is the radius actually. This is a positive number. So this ball of center as 0 is contained in the set of isomorphisms. And if we prove this, we are done, because this is the definition of an open set. A set is open if whenever we have a point in the set, there is a whole ball centered at this point contained in the set under consideration. So this proves the point A. And now this is just a corollary of the previous theorem. Because how do I prove this? I take an element here and prove that it's here. So I take an element in this ball, S, I call it S. So this means that the distance between S and S sub 0 is less than the radius. So when I do the multiplication, I get norm of S0 minus 1 times the norm of S minus S0 is less than 1. And now we use proposition 1.10. Okay, if we consider this operator, S0 minus 1 times S minus the identity. Now, I have to tell you that this really makes sense, because S maps E into F. So we go from E to F, and S0 minus 1 maps F into E. So this operator is an operator, a linear operator between E and E. Okay, so it makes sense to subtract from it the identity operator of E. So this operator now is an operator. So this is the norm in L of E. But I can factor by S0 minus 1. If I factor by S0 minus 1, I get S0 minus 1 times S minus S0, because S0 minus 1 times S0, or composed S0, is the identity, as you know. And by proposition 1.10, the norm of a product or a composition is less than the product of the norms. But the product of the norms is less than 1. So this is less than 1. So we have an operator now who is at a distance at most 1 from the identity operator, right? And what this tells you is that this operator is invertible by the previous result. Okay? But if this operator is invertible and S0 minus 1 is invertible, then S is invertible. Okay? So, therefore, S is an isomorphism. Okay? So here we are using actually the Banach isomorphism theorem, because actually, you don't need it, because you just read the previous theorem. Actually, you don't need to invoke the Banach, but it's helpful actually. Okay, so when I say that it's invertible, it means that it has a continuous inverse. This is what I'm saying. Okay, so this is just a corollary of the previous theorem, the geometric series expansion. Okay, so this proves the first part. Now the second part, I'll give it in the form of an exercise, because as I told you, I like to make students participate in the lecture, but now it's not totally possible. So how to prove that phi, this map, which is not linear, by the way, is continuous? So we have to prove that it's continuous at every point in the set of isomorphism. So we pick a point, an arbitrary point S sub 0 in the set of isomorphisms, and we prove that phi is continuous at S0. Okay. So we have to prove that phi of S minus phi of S0 tends to 0, as S tends to S0. So we take S in this ball that we defined earlier, and we let T to be the identity minus this. Or we can take actually S0 minus 1, S minus the same thing, it doesn't change anything actually. So we define T to be the difference between the identity of E minus this. And once again, T is now an operator from E to E. It's a linear operator from E to E, right? So T belongs to L of E. And now I will ask you to prove these points. First of all, T is well defined. And this is what I was trying to say, that this is an operator from E to E, and this is an operator from E to E, and therefore the sum or the difference is an operator from E to E. Okay. So this is pretty straightforward, but I wanted to you have always to check that we are mapping the space into the right spaces. Okay. For example, if I took S0 minus 1, then this would be an operator on F, not on E. Okay, so the order is important here, because here we go from E to F, and then we go from F to E, so we are in E back again. But if we start first as 0 minus 1, so we go from F to E, and then from E to F, then we are in F. Okay. So first thing, it's well defined as a linear bounded operator on E. Its norm is less than 1, and T tends to 0 as S tends to S0. Okay, because as S tends to S0, this tends to the identity. And if we write, and we can prove that actually S is given by S0 times the identity on E minus T, and therefore the inverse of S is the inverse of this times the inverse of this. Change the order actually. And finally, if you use this fact, so you just subtract S minus 1 minus S0 minus 1. Okay, you write this result as a series, and then you take the norms. You will have to prove this identity. And now we are done, because now this is a constant, and as S tends to S0, this tends to 0, so this tends to 0, and this proves the continuity of phi at S0, and therefore everywhere, because S0 was arbitrary. Okay, And that's it. So as I said, this phi is not linear, of course. It's just an extension of the inverse function 1 over t, which is a hyperbola. So of course it's not linear. And second remark, and last remark, in general, unless E is one-dimensional, the norm of the inverse is not the inverse of the norm. Okay, so cannot put here the norm of the inverse. It's not true. Okay, so this concludes this lengthy video on section 1.2. Now you can start doing the exercises because I covered everything you need to know in the exercises. And in the next video, I will cover section 1.3 about multilinear maps. And so thank you for your attention, and see you next time.